because what I'm going to talk about today is pretty related to what you might be doing there or not be doing there. So, how many classes of SDK did you have so far?
Only one, and it was like one thing only, just to have seen the program.
Okay. Do you plan to have more classes? Is it regular or is it just one?
Just one.
I think it was a one-off class. One was just a one-off class.
Yeah.
But we'll have more now with the CubeSat.
Yes, with CubeSat, so we have now
We'll have more.
Because let's not forget the big picture why we're actually doing all of this. We want to design missions. We want you to be able to design a mission, maybe. So in the sense like if there is an opportunity for a space mission, you need to do certain things. That's why you're using SDK to put a satellite into orbit, putting a ground station there and whatnot. And so here too, what I'm going to, let's say, bring you week after week is ideas you need to know to design a mission. So that's why I'm curious what you're doing in SDK. Just, and see if I'm repeating stuff you already know.
No.
Okay.
The repeating is mother of the learning.
Okay. Yeah, that's true. That's true. Repeating is important, actually.
Yeah.
Yeah. Yeah. So.
No, but will it be necessary for us to understand better more SDK classes when we give that feedback?
The thing is that all I'm saying will help you to actually understand or use SDK. So SDK is just a tool. Don't forget that. I mean, you can do mission design. I mean, in the 60s, SDKs didn't exist. Still, people were able to do space missions. So SDK is just a software, but it is indeed admittedly very helpful, very practically if you want, above all in an interdisciplinary class, if you want to have a quick feedback of whether the space mission is feasible and viable. But yeah, so that's. Yeah, I actually keep wondering if we should do some SDK ourselves again. But especially what I'm going to tell you today will be very technical, but will be indispensable if you want to use SDK. So actually the lecture today is entitled Orbit Determination, in the sense like in the first lecture we talked about orbit in general and we stick to the two-body case. We just have two bodies, the central body and the orbital body with the negligible mass. And we'll stick to that. We'll not introduce third bodies or whatever for the time being. But now we actually take the other perspective. Let's say if we want to determine an orbit, or the fact like we are on ground and we see something in the sky, whether it is a natural satellite like a planet or a moon, or an artificial satellite like a spacecraft, there's a certain set of techniques you need to know to actually determine its orbit. In the sense like, even if you, on a clear night, you are able to see with the telescope ISS, but who is able to actually now give you the precise orbit in terms of semi-major axis, eccentricity, periapsis, apoapsis, all the stuff we saw in the first lecture. So it's not so easy. Even if you see the ISS through your telescope, you're far from giving its eccentricity or perigee or whatever. So the purpose of today is rather on the observational side. It's more pragmatic. How do I do it in practice to determine the orbit? And so, yeah, the main part of this slide is 6. That's the key number in astrodynamics in general. You need 6 quantities to determine an orbit, and let's say to define the state of the satellite at a given time t. So we already talked about this a little. I mean, here's 2 ways how you can do it. Twice you have 6 quantities. In Cartesian coordinates, it's rx, or y, or z, vx, vy, vz, position and velocity. And then the famous Keplerian elements, which we're going to see this lecture. I suppose you haven't seen them, or have you?
We have seen.
We have seen that.
That's
a little
good.
bit.
Yeah.
If you have seen, then somebody can explain me what they are.
Should I?
Right now? Or we have a slide.
Okay.
I have a little quiz, who knows, and then you can say, I know. Yeah. But okay, that's what I'm going to talk about today. And here's the table of contents. In order to do basic orbit determination, which you see in the bottom of the two, you need to have a set of tool boxes, let's say knowledge. And that's what's in one. It's coordinate systems and measurement of time. This lecture might be the most technical, which we're going to do in quite a while, but you need to understand basic stuff about space and time to actually position a satellite in outer space. And it's actually the same things that SDK is going to ask you for input. If you set up whatever mission in SDK, you have to give them a certain coordinate system, a certain position and a velocity of the satellite, and a certain time. So you need to understand what exactly you are hammering into SDK, otherwise you just get results you don't understand. And if you don't want to use SDK, which a lot of purists, they don't want to use SDK, they want to do pen and papers, there too you need it. So
no one's looking at you, sir.
I mean, there is, in the space community, SDK is seen with, let's say, there's the one part who said it's the great tool, it's the best tool there ever was. The others are saying, yeah, if you use it, you don't understand what you're doing. And so it's, let's say, it's, how do you say that in English? It's cheating. Like you don't really know what you're doing, but you have a nice viewport and all of that stuff. So I actually like it, but there is the risk that you don't understand what you're doing. And if you don't understand what you're doing, you're lost.
So what would be the alternative?
GMAT from NASA, that's free. SDK costs a fortune. Then you have GMAT, GMAT, M80, that's for free. Then you have people who just code and write their own software. Meaning you start at zero and you code yourself your own SDK. By the way, the second book, I gave 3 books in the first lecture. The second book is from Valado, guys. That's actually the guy who coded SDK. You can see how closely Astrodynamics is to SDK, because one of the books I gave you, that's actually the father of SDK. So now I will talk about coordinate systems and the measurement of time. And here, yeah, don't hesitate to interrupt me, that might become technical. So I'll start with coordinate systems, and all I'm going to do now is to show you a few coordinate systems that are typically used when you're talking about space mission, referring or putting, referencing a satellite in space. And so what is a coordinate system? It's a reference framework in which information about the satellite can be stated. And most, I mean 99% of the time, is the position of the velocity. So now we're going to talk about reference frameworks. And depending on the orbit, depending on the mission, depending on the exact case at hand, you use a different coordinate system. I'm going to show you 4 now, or 5, I don't remember, 4 or 5. The first one is the so-called heliocentric ecliptic coordinate system. So I'm going to give one slide now per reference system. You'll find the same ones in the book, by the way. But it's not so easy to really understand what they mean, or at least the details. So here I always give a purpose, a fundamental plane, 3 key directions. I mean, after all, we are talking all the time of systems with the center, O, X, Y, and Z. That's all we're doing, but we're now going to change where O is sitting and what X, Y, and Z mean. So here is a case where O, the center, is sitting at the center of the sun, because it's a heliocentric ecliptic coordinate system. So the origin of the reference frame is at the center of the sun, and the main fundamental plane, X epsilon, Y epsilon, is the ecliptic. The ecliptic being defined as the plane that the Earth makes with the sun. You're familiar with that? So, and the main use of this reference system is for describing, of course, heliocentric orbit. If you have a satellite going around the sun, you need to have a reference system that takes care of that uses the sun as a central body. I mean, it's pretty obvious what I'm saying. And that actually is able to position your satellite with respect to the sun. For example, if you take a heliocentric orbit, it would be rather silly to take a geocentric reference system, meaning one where I put the Earth at the center.
So it's always the center. The sun is always the center.
The sun is always the center, and the fundamental plane is the ecliptic, meaning the plane defined by sun and Earth. Now, the key notion to understand is where is X, Y, and Z exactly pointing. And here, I was wondering, are you familiar with, anybody knows what solstices are and equinoxes?
What?
Solstice is like the longest day in the year.
The longest
Yeah.
shortest day.
When the moon,
And-
sun, and earth are both straight, something like that.
For example, what you see is the 4 seasons. I mean, you see the sun, and as an example, Earth. Earth is a satellite around the sun, so we can put it in a heliocentric coordinate system. And we see Earth here at first day of autumn, first day of winter, first day of spring, first day of summer. Now, for those not familiar with that, that's basic astronomy, but the seasons are a consequence of the fact that the axis of the Earth, of the pole, is inclined with respect to the ecliptic. For instance, if this axis here, I mean the one of Earth, was perpendicular like that, then we wouldn't have any seasons. I mean, I have another picture. Is this clear to you or not?
Yeah, but
Yes.
I'm wondering the distance in the eclipse is this. For example, the sun and the Earth is like this. The distance is a different, I think,
The distance between what and what?
between the Earth and the sun.
Yes. The distance is actually not exactly constant because Earth's orbit is nearly circular, but the eccentricity is not zero. That's why the distance is a little different as the Earth is going around the sun. It's not a circle, but close enough. But that's not so relevant for the seasons. What's relevant for the seasons is the inclination of this axis. So I have another picture somewhere later where you, at the very end actually. Here you can see the seasons, right? This is summer for the north. This is winter for the north. Why is it summer here? Because the northern hemisphere gets more sun than the south. Yeah. So this is the solstice in summer. That's when the Swedes celebrate midsummer, for those who know that party. Then we have the winter solstice, which we are now on our orbit around the sun. We are somewhere here. We are approaching now this. That's now in October. Then you have 2 equinoxes, meaning the day and the night are equally long. So, yeah.
So it's not the ancient axial tilt that changes, but there is position relative to the sun. That's
The actual tilt, that's very important. Does not change. It's always inclined like this. It will not do this for the time being. When we go into more complicated stuff, we'll tell you it's not. But for the moment, we say it is always inclined, let's say, to the right for the moment. It's always to the right and not to the left. So as it goes around, it stays like that. And as a consequence of this is that this situation is not symmetric to this situation. Because as you can see here, the north gets more sunlight. I mean, where even the whole North Pole, that's actually where we're having eternal daylight at the North Pole. And here we have eternal night at the South. So it's not symmetric.
so this is summer on the north.
Summer is always defined with respect to a hemisphere. Then it's of course fun. You have Martian summer, Uranus summer, and they are all different in length and in sun incidence.
But could you then say, like, due to the elliptic orbit, that the summer in the North Pole are warmer than in the South Pole, or vice versa?
Due to this little difference, I mean, so you want to dwell on the fact that since we are not circular, there might be a little difference. Okay,
So, but it's not noticeable.
The amount of photons you're getting is the same, you get them a little later. But it's really the angle at which the photons are going to hit Earth. You can see here, there's no photons arriving at the South Pole. And there's plenty of photons. I mean, it's a sphere, and only one half of the sphere is lit. If we switch off the lights and did the exercise with a balloon and a flashlight, it's always one half that's lit, and the other half isn't. And due to the fact that the pole is inclined, has to do with the angle.
So the
distance neglected.
Okay. Because it's not big enough, or does it not influence at all?
Eccentricity?
Yeah, it has to do with the eccentricity. It's asking, due to the fact that eccentricity is not zero, meaning it's not circular, is there a consequence on the seasons? My answer is negligible. Yeah, nobody talks about it. And, for me, it's just the fact that the photons arrive a little later because they have to travel a slightly bigger distance. And since the photons are traveling with the speed of light, doesn't really matter.
So they don't lose energy during the distance?
Not on that distance.
Okay.
If we now had a really elliptical orbit, let's say with a periapsis close to the Sun and an apoapsis at the wall there, maybe nobody has really studied this. I mean, after all, we are the only species studying seasons and just for ourselves on our planet. But it matters if you want to go, for instance, to Mars or to Venus or whatever. And when you're sizing your power system of a spacecraft, you need to know how much sun you get. Depending if you land in the summer or in the winter, it makes a difference. Imagine you land on a planet at local winter on that planet, and you're in permanent, at the pole, then you don't get any sun at all. So if you're designing a mission, let's say you wanted to do, I mean, a lot of people are talking about lunar missions going to the South Pole of the Moon, be sure that there's sunlight there. So all of that that was an excursion, but I was busy explaining in the first references. This guy. So it's the same figure, but with winter, autumn, without the colors and so on. But then, so the question is, where is X pointing and where is Y pointing in this reference system? And then my question is the quiz, this app, here you can read the answer, vernal equinox direction.
Is it possible to make it bigger,
Yeah.
like full screen, because it's even for me hard to see, I think.
By the way, you should have received the lectures.
Yeah,
Yes, we have.
Okay. So anybody knows what the vernal equinox direction is? That's the direction which X is pointing in this reference system. Have you, anybody heard about
It's
it?
Aries star.
Yes. Can you tell us a little more?
Because it's about the constellation of the Aries, which is so far away that have to be as a measure point to the whole system.
So for those of you who know about astrology in this case, it's Aries, which is one of the astrological signs which are linked to star constellations. And this direction here goes towards Aries. German, the Widder, in French, maybe I don't know. But typically nobody in here who is Aries, but that's the direction of the constellation in which this direction is pointing. Then we have the technically precise definition here. It's pointing to the position of the sun at the first day of spring at 12 UT over Greenwich Meridian. So if you're here, and it's the first day of spring, let's say you travel to London on the first day of spring, 21st of March, whatever year. Now you go on Greenwich. There is in London, you find a place where the Greenwich meridian is. Now you wait until exactly 12 noon UT. And then you have a look at where the sun is. That means you're here, you're looking where the sun is, then this, if you prolong it, it's exactly the direction. Of course, you would blind your eyes if you looked into the sun at 12 noon of Greenwich. But let's say you had a good filter in your telescope. Then you would exactly looking into this direction. That's the direction of reference we're using here. The others are simple. Y is just complementing the right-hand system, and Z is perpendicular to the ecliptic. So it's the X you need to understand.
Does the Z axis go to the polar star? Or is that relative to Earth?
It's relative to Earth. I mean, if at all, the question would be, is the prolongation of the axis of Earth pointing to the polar star?
No, this is the plane.
Yeah.
That would actually be the correct question. Then again, the answer is close enough. Yes. But the polar star, I don't know if have you ever tried to find it?
Yes.
You take the Big Dipper, and then you take 4 times, I think, the distance of the 5 times.
5 times the distance of what?
The distance of the, what do you call it in English?
Big beer?
Yes.
You know the Big Dipper, the constellation?
No, but it's a constellation. Yeah. Okay.
Yeah, and then if you take the handle of the Big Dipper and you prolong that distance 5 times in the right direction, then you end at a very faint star, which is the polar star.
Okay.
Polar star because it is in the prolongation of our Earth axis. But Z is not pointing towards it, because Z is just perpendicular to the ecliptic.
Yeah.
Yeah,
That's right.
that guy.
Okay.
So that's the first reference system. Again, the purpose is if you're convenient for describing heliocentric orbit, such as Earth, or I put a satellite there in blue, which is also turning around the sun. There's a number of missions as we speak which are turning around the sun. They're using that reference system. Next reference system is this, well, the geocentric equatorial coordinate system. Now, we just change our central body. This is convenient if you're using Earth as a central body. That's already almost it. Then the directions now are almost the same. X is still pointing into the same direction than on that figure. Still, X is still pointing towards the vernal equinox direction. Y is complementing the right-handed system, and Z this time is not pointing anymore towards the ecliptic. Sorry. But now indeed it's pointing toward the pole, the North Pole. So if you take this guy and you projected it on that figure, it would be a little inclined. I mean, X is still in the right direction, but Z now is now towards here, towards the North Pole. Both of these, the one I show here and the one I just showed, are inertial. Anybody knows what an inertial coordinate system is? Inertial means not accelerated.
Inertia.
Inertial, yeah. Meaning this guy does not turn with the Earth. I mean, Earth is turning, but X is not turning with it. See, X is still pointing towards here, and under, yeah, that's very important, because later we'll have one that will turn with Earth. But this guy still points here independently of what Earth is doing. It's like static inertia. This has some use later, because if you want to express Newton's equations, you want to do that in an inertial system, because otherwise you have to, I don't know if you saw that at some point in physics, if you're using a non-inertial coordinate system, you need to take into account so-called pseudo-forces like centrifugal force, Coriolis force, and stuff like that. This is why inertial coordinate systems are always useful when you want to express Newton's equation of motion, or precisely the one equation we saw in the first lecture, the two-body equation. SDK usually uses that guy if you want to propagate a satellite. Or that guy, but it will not use some other guys I'll show you later. Then another coordinate system is right ascension declination coordinate system. This is similar than the one I was just showing you, but it uses angles, namely alpha and delta, which you see on the figure. That's basically the one that astronomers are using. I don't know if anybody of you has a telescope. Anybody have to look at the stars. If you're talking to astronomers, they will say that this and this star, like what's the next one? The one where Breakthrough wants to go. Alpha Centauri, Beta Centauri has a certain right ascension and a certain declination. That means I is still pointing towards the vernal equinox direction, so I is actually still the one you saw in the two before. Here x, or here x in the 3 is the same, but now instead we just take the angle between this direction and here. So this is a star, some star you want to locate in the sky. Usually you need these two angles, alpha, the angle with respect to the x direction, and then delta, the angle with respect to the equator. Two more, and then we're done with reference systems. But that's kind of say, they are convenient for determining the position of a satellite with respect to the background of stars on the celestial sphere. So stars, since we are not doing astronomy in the strict sense, I mean we are doing satellite dynamics, so stars are considered fixed, as you were saying. It's really like they are, for our reasonings and at our scales, they are not moving, which is of course wrong, absolutely speaking, but they are moving, but they are so far away and that we can consider them as fixed. So they are useful means to position a satellite. If you just know that the satellite which you see moving, like ISS or any other satellite you see moving it very fast, you can say it's in this and this stellar constellation right now. So that's why it is sometimes useful to use a reference system that is actively used by astronomers. Yeah, just maybe on the first sentence I say, with respect to the background of stars on the celestial sphere. Anybody knows what the celestial sphere is?
The sky.
It's the night sky. Anybody ever had a globe with stars on it? I have wondered why do I have a globe with stars on it? I mean, are they on a globe? Of course they are not.
Some
I mean, the stars are not on the globe. But it's you consider, I mean, it's not, if you get an Earth globe, I mean, it's clear, it's Earth and there is London, there is Tokyo and so on, but if you have a star globe, you might wonder why to put them on a globe. Well, the globe is an abstraction of unlimited distance, so you consider them at infinite distance, and then you just put them all with respect to an angle you observe them. So you actually, if you put them on a globe, you actually put them all at the same distance on the globe. The same distance from the center of the globe, which is wrong, but it's a way of representing where the stars are, and that's the celestial sphere. Just I have a picture of it up here. That's the celestial sphere. You see, it's not. You take Earth, and if you ever go stargazing, star watching at a certain night, you will see the stars at some distance. And the globe you can buy in any shop. It actually represents how these stars are put. And here you see the same angles I was talking about, right ascension and declination. The same angles you just saw in this third reference system. So two more to go. Then we have the perifocal coordinate system. That's an interesting one. very convenient for describing the orbital motion of a satellite. Here we really take the fundamental plane is now the plane of the orbit of the satellite. It's not, for example, this guy here. For this guy here, the fundamental plane was the equator of Earth, of the central body. For this guy here, the fundamental plane was the ecliptic. And here, the fundamental plane is the plane of the orbital motion of the satellite itself, which might not be the equator, it could be whatever, depending on the inclination, which we're going to see in a minute. Just take that for a second. That's another convenient reference system with x, y, and z again. X pointing towards periapsis, that you already know. I mean, you have an ellipse, you can take x and point it towards periapsis, then you have true anomaly here, which you already know from. This is actually the reference frame closest to what you saw in lecture 1. X goes towards periapsis, then you have a certain angle, that is the position of the satellite with respect to periapsis. Y is perpendicular to the x, and z goes out. And then we have one final coordinate system.
It works.
That's a topocentric one. That's the last one. That's really the one you're using if you're an observer on Earth. So here, let's say we use it whenever we want to position an observer, like ourselves. If we are now, let's say, looking up and trying to find a satellite or a star, we use this one with directions, so it's also called SEZ, S, E, and Z. S stands for south, E stands for east, and Z stands for zenith. So if I had a compass here, I would know where north is. I don't know where north is here in this room. Let's say, for instance, it's there, then south is here. East could be here then. And zenith is always just the prolongation of where I stand. Clear? This is the last coordinate system I want to introduce. The purpose here is really, this one, for instance, is not inertial, meaning it turns with Earth. As we are standing here, and let's say we are turning with Earth right now, the coordinate system turns with us. Because it is linked to the very position, is attached to the position where we are right now, at a certain latitude and longitude from Greenwich.
How can any coordinate system created with the Earth as its center be non-inertial since the Earth is not accelerating in any way?
Can you say that again?
How can you have a non-inertial system? I assume you use the same definition they use in relativity. Non-inertial. What's the source of acceleration?
Right now, I mean, right now we are accelerated by the rotation of Earth. We are feeling a centrifugal, well, we are not feeling it, but there is one. Right now, right here. So, your question is this the topic of inertial coordinate system is a very controversial one. A good question would be to ask, can there be any inertial one? Meaning one that is truly not accelerated, that's really static. And then if you think about it, it's more philosophical discussion, but that it's the same notion as we're using in relativity, yes. But non-inertial ones, there's plenty of them.
The theory of rotation is not accelerating, it's of course velocity.
Yeah, but if you remember your physics at some point in the bachelor, I don't know where, I mean, even for a constant angular velocity, you are feeling a centrifugal axis. If you go to the Schirmerfoer, I don't know, or Disneyland or whatever, you are in such an attraction, how you call it, in such a game, where you are turned around, but you feel that you are pulled outwards,
So constant
even if the thing goes at constant velocity. Of course, you're feeling it even more if the stuff accelerates.
Yeah.
Rotation is actually also a constant acceleration in one direction.
Yeah, rotation is a constant acceleration in one direction. That's the French say MC, mouvement circulaire uniforme, uniform circular motion. If you look it up.
So constantly being accelerated downwards.
Yeah. So this guy, yeah, non-inertial because it turns with us, but very useful because we can finally use north and south, I mean the compass, to position ourselves. We're getting back to all of these. They are just tools which you also find in SDK. Sometimes we should really use them. Now, big moment for today, Keplerian orbital elements. So I just showed you 5 reference frames. Now I want to talk a bit about Keplerian orbital elements. So you said you knew, you could explain it a bit.
The Keplerian elements are the 6 elements which define the apogee, the eccentricity, then we have the semi-major axis, 3, the true anomaly, the descending or ascending node.
What is it?
That is where the orbit is crossing the vertical plane of the Earth, for example.
Yeah.
And then we have the inclination.
You mentioned one that was not. It's good
Apogee
enough.
was
Apogee was
not
not it.
So,
But good enough. I mean, we can start with it. So here they are. This is probably the most important for today, and you just need to understand it. A is the semi-major axis. You saw it in lecture 1. I mean, the first 2 ones, you actually saw how we established them in lecture 1. A and B. They shouldn't be new. The new ones are I, omega, capital omega, and small omega.
True anomaly.
True anomaly
Yeah,
solved.
recently.
So you solved the first 2 and the last one in lecture 1, but you get 3 new ones, which are triangles you just need to understand. The most difficult one I can tell you right away is big omega. So anybody can tell me, let's go, one after the other. A, the semi-major axis. Somebody can tell me what this is? What's the semi-major axis?
Diameter of the
No, it's half of. It's not diameter, it's half of diameter.
well, actually it's half.
Half of the, let's call it the diameter of the longer part
Yes,
of
the
the
longer
ellipse,
part, yeah.
because the other will be the semi-minor
Minor.
axis, so the semi-major axis. Let's say for the moment that we mostly have, usually when you talk about orbits, you mostly have in mind an ellipse. But you need to be aware that even parabola and hyperbola have a semi-major axis, which are
Why do we need this parabolic and hyperbolic? Because I cannot imagine that the bodies can move.
we get to that, but if you don't have parabola and hyperbola, let's say for instance you have a central body and you're going around in an ellipse. Actually, it's the one part in the first lecture I couldn't do due to time, but if you want to quit your central body, let's say you are on Earth, you want to go to Mars. You need to liberate yourself from Earth gravitation, go out, and then you get captured by Mars, and then you'll turn here. So let's say, for instance, this is Earth. I am on an ellipse. Now, I will be there forever. Let's say I have a satellite that was launched in an ellipse. Now, let's say we have a propulsion system on board. Of course, let's say even Earth, let's say I'm the Sun, this is Earth. If I want to go to Mars with this guy, I need to wait for the right window, because this guy should be somewhere here. Let's say that happens, and now I give a boost, I burn, and then we go out, and now we are actually on a hyperbola or parabola.
Okay.
You can't do it on an ellipse, because whenever you change central body, you go on a parabola and ellipse. Now we are on a parabola, let's say we are on a parabola, and here now I'm doing another burn. I'm slowing down with my propulsion system, and I get captured in another ellipse. That's how you do a transfer from one central body to another one. That's stuff we do in semester 2.
Okay.
Because we need to combine all these ellipses and parabola and hyperbola into a conceptual framework where we can go where we want to go. But for the moment, we are just turning around here. You need parabola and hyperbola, but there's this little trap that if you talk about orbits, in 90% of the time, people think about ellipses, which is good enough if you are in a CubeSat in Earth orbit. That's an ellipse until it dies in and burns in the atmosphere. But if you want to do interplanetary stuff, you need the others.
I have one question that might be off topic. The Hubble telescope. Is that a telescope on Earth or on space?
It's in space.
And is it orbiting around Earth or?
To help, let's say, where's my Earth? Okay, I took Earth, Here you actually need these reference frames to understand it. But in short, the Hubble telescope is a telescope in low Earth orbit. I don't remember if it is at 500 or 1,000 kilometers, but pretty close. It never goes up. It just goes around, and since there's not the attenuation of the atmosphere anymore, that's why we actually do it. A space telescope, the one purpose is that you don't have the atmosphere that's attenuating it, so you see much further. And so now, basically, let's say this is the opening of the telescope, just looks in the same direction all the time. Now, with the use of your attitude control system, you can change the pointing. It's there, and it's always looking there. Even if it is there, it looks up. So it's not turning around like that, which you could do too, but that would be stupid for your observations because you don't get a constant fix on the star. So you keep it fixed. Yeah, that's Thomas Webb and the James Webb too. There's some other ones. And here the question on what orbit you're going to put it in terms of A, E, I, big omega, small omega is important in your mission design. It depends on what kind of field of the celestial sphere you want to observe. But it's okay, we did A. I mean, let's do the second one, eccentricity. Anybody can tell me what this is? Should be clear.
The shape of
the orbit.
orbit.
And in case of a parabola?
One.
Parabola is one.
And
Parabola
More than
bigger
one.
Inclination
The
angle.
the angle.
between.
The
Now, because now we got 3 angles and you need to understand.
Yeah.
This is for sure in the exam, I can tell you already now. If I would be kicked if I don't put that in the exam. I mean, it is just clear, you need to understand these 3. So,
Yeah, just the surface and the equator.
yeah.
And
No, not between the surface, between.
the orbit.
Here you have an example actually. Here you see I is here.
The periapsis direction.
See here, okay, let's take the figure. You see, the orbit is shown with this hashed. I mean, that's the orbit. It's marked with the dark like that. And so, as you can see, the angle between Earth equator, let's say this rectangular guy is actually just the plane of the equator. The angle between the equator and that orbit is I, which is the same than here. They just put it here, but it's basically, as I was saying, the angle between the equator and the orbit. Then you can see immediately if you are in a polar orbit, then I is what? In a polar orbit, meaning you're going to go over the North Pole all the time. I is 90. If you're in an equatorial orbit, I is 0, like what SES does. SES has all its orbits in equatorial or close to equatorial, meaning with an I close to 0. And can somebody tell me, let's do a little first element of mission design. If you wanted to do Earth observation, let's say you wanted to do a spy satellite, which a lot of countries are doing. What eye are you going to choose for the inclination?
Polar, maybe a 90 degree.
Because, let's say you... we should have a globe. Don't think I'm serious.
Yeah.
This is the globe. This is North Pole, South Pole. I mean, of course, my orbit is going to turn like that. If it is polar, as you were saying correctly. And now Earth is turning underneath.
Yeah, it's rotating.
So I'm staying on the same orbit, and as Earth rotates, if I'm pointing my telescope downwards towards Earth, I can see everything.
Yes.
If, however, I put my satellite equatorial with an I equals 0, then my satellite is going to turn like that. Okay, and the Earth at the same time is going to turn like that. But since I'm pointing my telescope downwards, I will never see what's going on at high latitudes. Can you see that?
Hi.
So if you're doing mission design, you need to say, okay, what eye do I need? And so it continues. What big omega do I need? What small omega do I need?
But in this, like if you're wanting like a country in the North Hemisphere, half the time you won't see it too, right?
Say that again.
If you want to see a country in the North Hemisphere, like half of the time you won't be able to see it too because you're
Yes.
yeah. So
That's why your A becomes important, because we had a formula in the first lecture what the period
oh,
is.
then you stop there.
If you are closer to Earth, then your period is small and you do a lot. And you have a lot of revisit time. But if your A is large, you have the formula in your first lecture, then your period is slower and it takes you damn lot of time until you are again at the northern hemisphere.
Okay. Yeah.
Which could be interesting, because imagine you just want to spy on a country in the it is really what's done. If you want to spy on a country in the northern hemisphere, you don't care about the south hemisphere. In which case you do not, you play with, you always play, these are 6 levels with which you're playing. So if I want to spy, we have the spy example now, I could do other ones.
Yeah.
I could do, let's say you want to observe the rainforest in the southern hemisphere, that we have more lower road, equally important. Let's say we want to do that, then I don't care about the northern hemisphere, in which case I'm going to do a bigger eccentricity, meaning my apogee is farther away than my perigee. And due to Kepler's second law, I know that I spend more time at the apogee, whereas on the perigee I go quicker.
Yeah.
So,
Yeah, then you play with it,
We spend longer time.
so you have these different tools, and these are the 6 you need to play with in order to do a good mission. If you do a really bad mission, you can do it really completely wrong. If you want to look at the Amazonas and you put you put your apogee high north, then you don't see it at all. So, but maybe now big omega. Who takes that one? That's the most difficult one. Right ascension of the ascending node.
It's also an angle. So if this would be the inclination, this would be the omega then. So it is where the orbit is crossing twice the, or on the ascending side, the equatorial orbit.
This guy. Why am I saying it is the most complicated one? Because you need to understand the vernal direction. If you don't, you see it's always with respect to the Arias point I showed earlier. This, actually the coordinate system I'm using here is the geocentric one I have been introducing here. Yes. I mean, this direction is the vernal equinox direction. You can see it again on the other figure. So, omega is always defined with respect to the vernal equinox direction. Capital omega. Final one, or almost final one, small omega, called the argument of perigee. Anybody?
Is at what point perigee is, so the angle between the ascending node and then the perigee. The perigee is the closest point to Earth.
So we know what perigee is. It's in an ellipse, the point that's closest to the central body, meaning Earth. And this perigee can be anywhere here on this orbit. So in this example, it is here. So. But you could imagine that that small omega is 0, in which case perigee lies on the plane of the equator. You can even imagine what happens with the circular orbit. We don't have a perigee. So then small omega becomes undetermined, which is something we want to avoid. That's the drawback of Keplerian elements. The advantage is they allow you to visualize in 3D where we are. The disadvantage is, depending on the case, you get mathematical indeterminations, in the sense like for a circular orbit, small omega doesn't exist. In case of what else we have. Okay.
Sorry, could you repeat the advantage?
The advantage is that it is supposed to be an intuitive way to define an orbit. It's much, if you have Cartesian, X, Y, and Z, we do exercises on it, but it's much less intuitive than using these 6 guys. Because if I, using Cartesian coordinates, if I say the position is 1, 2, 3, and the velocity is 0.5, 0.9, and 1.2, you don't know anything about the inclination, you don't know anything about the semi-major axis, and you don't know if it's a circular orbit or not. Here you get a lot of information. Then the final one is the true anomaly, which we have already seen. Then in the bottom, I'm giving a few other ones. Not so important, but for you to know, from time to time, the 6th one, the true anomaly, is swapped by either the time of periapsis passage, the argument of latitude, the longitude of periapsis, or the true longitude of These are more technical stuff. Has to do with that from time to time parameters are not defined. For example, for an equatorial orbit, you don't have a capital omega, because there is no ascending node, because you're equatorial orbit. So here I invite you to really study this in depth and understand it.
I'm sorry. I didn't know exactly the omega, big omega.
Big omega, what's the use of it? The use of it is to position, we need some pictures, it's to position your orbit with respect to the fixed stars, with respect to an inertial frame. That's why, what can I show that? I mean, let's say this is Earth. Oh, I don't have any. I need more tools to show them. I'll bring other tools next time. It is the one that defines the orientation of your orbit in so-called inertial space, meaning with respect to the stars. And that, I agree, it's not, that's why I'm saying it's the most difficult one to grasp. It's not so obvious to see that. Let's say this is, okay, here we have periapsis. And let's say the certain star configuration is towards there. Then if I have a bigger omega, for instance, let's say it's there, then periapsis is not looking towards there anymore, but towards there. And so with respect to the inertial of the celestial sphere or the stars, the orientation of your ellipse is different.
What was I exactly? The coordination.
I?
In the coordinator system.
I.
Yes.
It's the geocentric coordinate system. So that's why I'm saying you need to understand what the vernal equinox direction is. I think I have another picture actually. That might help. Here.
Oh, it's the position of the sun.
See, if my, let's say this is my orbit. It matters if my orbit is like that let's say this is the plane. It matters if it is like that or if it is like that. So it's with respect to this vernal equinox direction which you're seeing here. Here, the Sun, you have our Mercury, Venus, Earth, Mars, and so on. And the vernal equinox direction is one direction which is fixed with respect to the stars. And so it matters, let's say, we take a heliocentric orbit. Sun is the central body, and let's say this is, I put it like that. Here, my, let's say, my periapsis is this side, my apoapsis is this side. Here, my apoapsis is pointing exactly in the vernal equinox direction. But if I now change that like that, and let's say this would actually have to go on the other side of the TV, we need to actually have some 3D imagination or visualization here. Then my orbit is different. It's this orbit, let's say this part goes through the TV and comes out on this side. This orbit is a different orbit than this one. So it's a rotation with respect to the vernal equinox direction, and that's a capital omega.
PowerPoint it has written that it's pointing to the position of the Sun at the first day of the spring, and we consider it fixed because it's an inertial coordinate system. So, okay, I can catch it.
So, yeah, I mean, we are on Mercury, so the green one is Earth. Sometime in spring, we are here on the green. Now, let's position ourselves on Greenwich, meridian, and wait for noon and look at the Sun. Then if we prolong, that's the vernal equinox direction. And omega, big omega, is the orientation of your orbit with respect to that direction. It's the position of your ascending node. That's the most difficult part of the capillary analysis.
Can I ask a question? In respect to the big omega 2, if we have a circular orbit in the equatorial Earth,
Yeah,
in this case, in this case, what would be the right ascension of if we are in the same plane of this direction?
Then you have a problem, you're right. That's what I was saying. If you have an equatorial orbit with an I equal to 0,
yes,
then you don't have an ascending node. And if you don't have an ascending node, then you don't have a right ascension.
Oh, then we don't have. Okay, I thought it was the other one again. So it's this one that we don't have. Okay.
Okay. What time is it actually? I need to do a break. I almost half time.
5:35. 5:35.
5:35. Let's do 5-minute break.
Okay.
I have to go in the car.
Here's a great question. It's so hard to visualize.
Yeah, it is hard to visualize, and you need. That's why SDK is good. But if you're in the beginning of SDK, you are asked to put in these parameters. If you don't know what you put in there, then you're lost. But there's some nice movies. I tried to find some videos, but what helps most is if you have a globe, actually. A real classical globe, and then you take a plane, for instance, like that, that's your orbit, and you try to see the different, I mean, inclination, if this is the equator, inclination is this, the angle, like, I mean, this is an equatorial orbit, this is a polar orbit.
And here is the periapsis.
And the big omega is this. I keep I constant, but I rotate like that.
Okay.
So I'm back in a minute.
So it's just rounding with the same inclination.
Yeah, it's inclination, and that's the argument of Perigee.
Last this week. Okay.
बहुत गुस्सा है तो मुझसे तो हफ्ते में एक बार आता है फिर खुल नहीं खाता
मतलब प्रेयर जाने के बाद हम लोग की पहले होते ना एक हफ्ता तो क्या मेरे को ज्वाइन किया लास्ट वीक फिर हफ्ता हुआ
वो तो मैंने करा
How to get to call
आज कैसे प्रेयर का प्रिपेयर किया मैंने करा
Have to print this picture and put it on the wall. This one is the best.
Well, I think I was looked at this picture so many times that I already have an idea.
Yeah.
But not in 3D sometimes difficult. And then with this at least I'm more or less happy. We finish at 6:30, right?
quarter past
6:15.
6:50?
Yes.
Just in half an hour?
Yeah.
Yeah.
Page 10.
Yeah.
A lot of things.
We will be faster.